Have you ever run a piece of code and watched your browser completely freeze? Or stared at a maximum call stack size exceeded or out-of-memory error in your console? These errors occur because JavaScript code requires a runtime environment to function. Take a look at this archival photo from a Google presentation. You can see V8 listed right there. V8 is a C++ program acting as the brain of the browser, translating your code into physical machine operations. Because JavaScript is a high-level language, this engine handles the manual labor of memory management for you. This diagram illustrates the engine as a factory, divided into two distinct zones, a conveyor belt for executing code and a massive warehouse for storing data. Mastering the language requires understanding exactly how this factory operates. Traditional compiled languages translate their entire codebase into binary long before the program runs. JavaScript uses a different approach called just-in-time or JIT compilation. During the JIT compile phase, the engine scans the script milliseconds before execution. The compiler extracts declarations from the text to map memory needs. This pre-execution mapping is hoisting. The engine physically moves declarations to the top of their scope container before any code runs. This pre-execution memory map makes hoisting a predictable, logical byproduct of the engine's optimization process. The call stack manages execution contexts, storing primitive values in its trays. Complex data uses the memory heap warehouse, connected by a pointer back to the stack. Recursive functions without a base case cause these contexts to stack infinitely, hitting the engine's memory ceiling. A maximum call stack size exceeded error is a protective limit. The engine stops the process to prevent a catastrophic system freeze. Let's test this mental model. On the left is a 5-line JavaScript snippet. Pause the video and map out where the primitive variable, the object, and the function call belong on the blank workspace on the right. Here is the solution. Primitive values stay locked inside the stack trays. The object is stored in the heap warehouse with a pointer connecting back to the stack. Finally, the function call creates a new execution context tray on top of the stack. As programs run, contexts pop off the stack, leaving behind orphaned objects in the heap. To reclaim that space, the engine relies on the garbage collection system. Mark and sweep identifies what to keep. A green signal from the window root travels down pointers, illuminating reachable objects. A sweeping laser then vaporizes unlit blocks. However, poorly managed closures can maintain hidden references, forcing massive objects to stay green and survive the laser indefinitely. Modern JavaScript uses weakmap or weakset to maintain relationships with objects without preventing them from being garbage collected. Most modern memory leaks are logic failures by developers, keeping data reachable long after it is needed. At peak efficiency, the factory runs in harmony. The JIT compiler parses the text, the call stack pumps execution contexts, the heap stores heavy objects, and the garbage collector sweeps away the unused data in a continuous rhythm. This architecture consists of 4 core domains: JIT compilation for translation, the call stack for execution, the heap for storage, and garbage collection to reclaim memory. Understanding this underlying architecture allows you to anticipate exactly how the engine will allocate, execute, and destroy your code.